Hi, my name is Pavel Veselý, and this talk is about competitive ratio of longest queue drop. It is a joint work with Antoniadis from Twente, Matthias from Warwick, and Nicolaos. Let me start with a definition of shared memory switches model, which is a buffer management model. So we have a simple network switch, which has an input port, a buffer for storing up to m packets, and several output ports. Basically, we think of like unbounded number of output ports. To this buffer, packets arrive. Time is discrete, consisting of time steps, and in each arbitrarily many packets arrive, and these packets are characterized just by the output port to which they are destined. So they have the same size and the same priority, the same value. And after packets arrive, in each step, each non-empty output port transmits a packet, where non-empty means that there is at least one packet for that output port in the buffer. And now we want to design an algorithm that will reject or accept each packet that's incoming to the buffer while maintaining the capacity of the buffer. And if it accepts the packet and the buffer is already full, then it can evict some previously accepted packet from the buffer. And these rejections or evictions are irrevocable. We cannot take the packet back. And the goal is naturally to maximize the throughput, which is the total number of transmitted packets over all steps and queues. And since kind of the packets are characterized just by output port, then we can imagine that there's a queue for each output port in the buffer. So the queues are here on the x-axis and their size on the y-axis. So we have 6 queues, and the total size of these queues must be at most n. Now let's say a new packet arrives, it does not fit to the buffer, so we can either accept it or reject it, or we can also evict some other packet. And since we are in the online world, we don't know where packets will arrive in the future. We don't have any information about future arrivals. So it seems natural to evict a packet from one of the longest queues, because they will run out of packets at the latest among these queues, if nothing arrives. And this evicted packet could also be the incoming packet. And if there are more longest queues, then we just choose arbitrarily. And this is the longest queue drop algorithm. So we are interested in the performance of this algorithm, and we look at the worst case behavior, which is quantified by the competitive ratio, which is the worst case ratio over all instances between the total number of packets transmitted by an offline algorithm that knows future packets arrivals and a number of packets transmitted by LQD. So here's an overview of previous work. LQD was introduced in the 19th, and about 10 years later, Hane, Kesman, and Mansour showed that it's too competitive, which means that this ratio is at most 2. They also gave an example that the ratio is at least square root of 2. Then there has been some progress in special cases, like when the buffer size is small, or when there are just 2 or 3 output ports. Let me just point out that this 1.5 is probably not tied for 3 ports. And quite recently, there's been a better example, like giving higher ratio, slightly higher than square root of 2. And our new result is that we can show that LQD is 1.7 competitive, and this improves upon these 2, and it's kind of in the general case for any number of output ports and any buffer size. So what is this strange number? It's slightly smaller than 1 plus 1 over square root of 2. It's defined like this. It's 1 plus 1 over a row for a row defined using this nice equation. So that's just something that comes out of the analysis. Why are we interested in this longest queue drop algorithm? First, it's one of the fundamental problems in online buffer management, and I would recommend the nice survey by Goldwasser, which is about 10 years old, but it's still up to date in most cases. Also, this LQD algorithm is very natural to derive for shared memory switches for these queues, and is actually the only known competitive algorithm for this problem. And third, since LQD tries to balance the queue sizes, it kind of tries to achieve a fair distribution of packets among queues. So maybe there's some application in a fairness setting. So in the rest of the talk, I would like to first give you some intuition on how hard instances look like, and I will quickly go through the simple proof of two competitiveness from previous work. Then I would like to show you how the queue size, the size of one queue evolves over time, and I will then go through the analysis using some simplifying assumptions. When I started looking at this problem, I thought that it might be possible to prove the square root of 2 directly, and we kind of made the natural assumptions that on worst case instances, the buffer configuration stays the same in every step. What do I mean by that? So here we again have queues on the x-axis, their size on the y-axis. LQD sizes are drawn in blue, while the adversary has queues in red. So basically, there are some balanced queues where LQD has more packets and the adversary has just one, whereas here the adversary has more packets. And using these natural assumptions, you can actually prove relatively easily that LQD is square root of 2 competitive, using the ideas that I will show later. But this assumption is not correct, as this lower bound shows. And if you look at this new paper, you can see that on their instances, the maximal size of a queue for LQD fluctuates a lot. It grows faster and faster, and then it drops rapidly, and this repeats. So this is some intuition on how hard inputs for this problem may look like. So let me go through the proof of two competitiveness which is like 20 years old. So the first question we need to ask is how does the adversary gain extra profit compared to LQD? And that's by transmitting extra packets, which are packets transmitted from queues that are empty from LQD. So, for instance, in this step, there will be 4 extra packets transmitted from these 4 queues. Now, what they show is that the total number of extra packets over all steps is at most the total number of packets transmitted by LQD. And this applies to competitiveness because the profit of the adversary is at most the profit of LQD plus the number of extra packets. So how do we show this inequality? We basically maintain a matching from potential of extra packets to LQD packets in the buffer transmitted. So potential of extra packets are those that have position higher than the size of this queue for LQD. And this matching can either go to LQD packets in the buffer or even LQD packets that are transmitted. So why such a matching exists? Let's say that there are new potential of extra packets in this queue, which means that LQD has rejected or evicted some packets from this queue, which means that the LQD buffer is full, and so the number of LQD packets in the buffer is definitely higher than the number of potential extra packets in this step. And also, since there are some packets rejected or evicted from this queue has maximal size or maximal size -1. Kind of the position of every new potential extra packets is at least the size of any queue for LQD. And using these ideas, you can show relatively easily that this inequality. And in our paper. We show a slightly stronger inequality than here. We show for some row bigger than 1, we show that the row times the number of extra packets is at most the LQD profit. And this implies that the competitive ratio is smaller than 2. In this talk, I will make one simplifying assumption that there are no LQD extra packets, which are defined similarly just with opt and LQD swapped. So this is kind of the extra profit of LQD. It's tempting to make this assumption without loss of generality, but we could not prove that this is without loss of generality, and might be not without loss of generality actually. So before going through the analysis, it's useful to look at the life cycle of a queue in kind of a typical case or in instances that look hard. So this queue is empty for some time. So now the time is on the x-axis. So this queue is empty for some time until it gets first packets. Let's say LQD accepts 5 packets, whereas the adversary accepts just one. And this configuration remains kind of the same. So the adversary has just 1 packet in this queue, but the size for LQD goes up and down, like in this instance from the new lower bound. And then at some time TQ, queue overflows, which means that some packets are rejected or evicted from queue, while the adversary accepts more packets. So there are some new potential opt extra packets here. And this time is important because there are these new potential extra packets. You can kind of assume, or in a typical case, the adversary has just 1 packet before TQ, while so there are some new packets arriving to this queue in each step. Well, starting from TQ, no packets arrive to this queue, so its size slowly goes down for both LQD and the adversary, but LQD runs out of packets sooner, so the adversary transmits some opt extra packets then. And what we do in the analysis, we take TQ as the last time when Q overflows, so when there are new potential extra packets. And we can assume without loss of generality that once a queue gets empty for LQD, it will not receive new packets in the future. And that's by that we have unbounded number of queues, so these new packets may arrive to a different queue that's not used yet. Okay, so we would like to show this stronger inequality for some row bigger than 1. We show it by splitting this LQD profit among all queues such that row time, number of extra packets transmitted from the queue, is at most the LQD profit assigned to this queue. So how do we split this LQD profit? So the first idea that you may have is to split the profit proportionally to the number of extra packets in this step. So this is relatively simple. Anyway, so when potential extra packets get some profit, they will transfer it to the queue in which they are in. So this is simple, but it's only sufficient for row equal to 1, which only implies 2 competitiveness. And this is because a queue may only have 1 extra packet and 1 potential extra packet once it overflows for the last time, while LQD has relatively long queues, which kind of means that this profit assigned proportionally will be small. So we are able to fix this flaw by just giving more to queues that have relatively few extra packets. And how is that achieved? We basically give directly to queue an alpha fraction of packets transmitted from queue when it's dying. And it's dying once it overflows for the last time, for the rest of the time. So, and alpha is a parameter of our charging scheme. And the remaining profit that's not given directly, it's still split equally among all potential extra packets. So from queues that are dying, which means that they have overflown for the last time, alpha fraction is given directly to Q, while 1 minus alpha fraction is split equally. And profit from live queues that will overflow later is split equally. So we would like to show this inequality, and we would like to get some lower bounds on the profit that we assign to this queue. And the profit assigned directly is kind of simple to analyze. It's just alpha times the number of packets that are transmitted from queue since the time when it overflows for the last time. So when it is dying. The main challenge is analyzing this profit assigned proportionally and defined notation. So ET is the total number of potential extra packets over all dying queues, and ETQ is the number of potential extra packets in a particular dying queue. And so each dying queue gets this fraction of profit not assigned directly. So we would like to show a lower bound on this. And in particular, we would like to show an upper bound on this ET. And that we do using a new quantity that's called sigma t. And that's just average size of live queues. That are queues that will overflow in the future and already have some packets. So our upper bound on ET is this. It's sigma minus 1 times LT, which is the number of, and LT is the number of live queues. So proof by picture. So the idea is that when new potential packets appear, the LQD buffer is full. And if you subtract this like common part of the buffer configuration, where both opt and LQD have packets, then because LQD buffer is full, this blue only part must be larger than this red only part, and this red only part are the potential extra packets. And the size of the blue only part is sigma minus 1 times LT, assuming that the adversary has 1 packet in each queue. It has at least 1, since we assume that there are no LQD extra packets. So that's the upper bound on ET essentially. Okay, so we would like to lower bound this profit assigned proportionally, which is this fraction, and the fraction of potential extra packets in this queue, times the number of live queues plus 1 minus alpha times the number of dying queues. That's like this is the profit assigned proportional. So we have already an upper bound on ET, and we would like to get a lower bound on DT. And this is our lower bound. So it also depends on the number of live queues, and it's multiplied by a difference between sigmas. So this is 0 if sigma decreases or remains nearly the same. So it's only useful when sigma increases, and I will tell you why in a moment. So how do we show that? So let's suppose that the set of live queues does not change. Then if this difference of sigmas is positive, that means that number of packets in live queues must increase by actually this quantity. And the only way it could increase is that LQD must transmit at least the same number of packets from dying queues. And that's because no packet is rejected or evicted from a dying queue. Okay, so the actual proof is more complicated because the set of live queues may change, and we also get this -1 because the overflowing queue may have 1 less packet that the value of sigma. Okay, so we have these two lemmas, and using these two lemmas on this profit assigned proportionally, we get that the profit assigned proportionally to the queue in each step is this nice fraction. And now the challenge is to lower bound the sum of this fraction over all steps from the step when Q overflows from the last time. So when it becomes dying. Basically, this fraction gets smaller when sigma increases, and we kind of rectify this increase using this lower bound on dt. And we also want to connect this like profit assign proportionally with profit assign directly. That's by this observation that the size of the Q when it overflows for the last time is at least, because it overflows, it's at least maximum size -1, and maximum size is at least the sigma. So now we have connected the CQ to these sigmas here, and we also want to show how this ETQ evolves over time, and once this cube becomes dying, this ETQ typically remains constant for some time until the Q becomes empty, and then it decreases by 1 in each step. And using these observations, we had lots of fun with lower bounding this sum for like a worst case sequence of sigmas, and in the end we could take rho roughly 1.1 in this inequality at the top, which implies that LQD is about 1.9 competitive. So this already shows that LQD is better than 2 competitive, but it's not quite the result that I claimed at the beginning. The bottleneck in this analysis is actually quite surprising. It's this -1 in this lower bound on dt. And that's, as I said, because an overflowing Q may just have sigma t -1 packets, because sigma could be equal to the maximum size of a Q. It's a bit this -1 is a bit annoying, but it actually turns out that we can get rid of it essentially, and using some slack, and the slack is when sigma decreases. When sigma decreases, then this lower bound is just 0, and sigma decreases typically when new active Qs appear, and that eventually leads to defining a potential, which is alpha times the number of active Qs that will overflow in the future. And with this potential, we can get rid of this -1 here, but it makes the analysis quite more complicated, because we need to analyze the instance by phases, which are time intervals between these steps TQ. And now the case of decreasing sigma becomes kind of the bottleneck for the analysis, and it's very technical. And also, I was assuming in this talk that there are no LQD extra packets transmitted. And as I said, we could not show that this is without loss of generality. So in fact, what we do is we match each transmitted LQD extra packet with one transmitted extra packet, so which cancels it out, and we do the analysis just for the remaining extra packets. Okay, that's all I want to tell you about the analysis. Be happy to answer more questions. So to conclude, we can show that LQD is roughly 1.7 competitive, which is the first constant upper bound better than 2. The best lower bound is slightly higher than square root of 2. And LQD is the only non-competitive algorithm for this simple problem with Qs. So the first open problem is obvious. There's a gap, and I would say that both of these bounds are not tight, and definitely our upper bound is not tight. And let me just point out that maybe we can tweak the analysis somehow to get a slightly better ratio, but substantial new ideas are needed for, let's say, 1.6 competitiveness. So if we are not able to determine the competitive ratio of LQD, maybe we can show indirectly that it's the best possible deterministic algorithm. And also randomized algorithms for these problems have not been studied yet. And this area of online buffer management has many more nice open problems. And I again recommend this survey by Goldwasser. That's it. I'd be happy to answer questions at iCalp or by email. Thank you all for watching.